Okay, thank you. We have just about an hour, I think, or slightly more. And this is the last fairly intense session I'm going to run. I will be off your neck next week, so please take it from me, okay? There will be a lot of material, just because I like to finish off many things that came up, lots of interesting things. Okay. All right, so let me begin with, is everybody here? Okay. So look at this little animation. What is that? That's my quickest attempt to make an n-body using the GD library. So I got n-body serial code from somewhere, and one of my colleagues, research friends at the University of Delaware said, hey, I teach n-body always with, or anything, diffusion, heat diffusion with graphics. So there's a library called GD that you can install the print state statement, or in addition to the print state statement, you can sort of so put those. This is a complex series of commands. It's fun to learn this library. So I highly encourage you to start learning this library whenever you can. You have to install GD, then you have to generate an MP4 video, and then actually you have to write out the GD format and then convert it to a video MP4 using FFmpeg. So there are 3-4 software items. I can publish the instructions. Okay, when you do that, you can make movies out of your HPC. It's not good for timing, but it is good for fun, watching what happens in science and all that. So Steve Siegel has heat flow diffusion simulation where the rod gets a red and then the redness goes. That's fun. The other favor you have to do to me is exercise your brain to load the data back from your main memory back into your L3, L2, and L1 caches, i.e. you had to do a little what we call a test. This is the best test. I wish I had such exams when I was studying. You can ask anybody, you can look at your slides, but don't get a free answer and write it down, just understand and answer, okay? So we want everybody to succeed, so a discussion through all the topics is what is in there. So maximum drowsiness, take a payasam before doing it, okay? Pardon my typos, that's because I had too much of it. And just to keep you motivated, this is one of the questions. A megawatt of power drawn over a year costs this much in India with electricity at ₹5 per kilowatt. Calculate the number of hours in a year multiplied by 1,000, etc. Is it 4.2 crore rupees, or is it 42 crore, or 4,000 rupees, or nothing? I'll play Karodpadi and power the machine. Okay, so you chose the answer. So just to keep you awake and going, that's how the questions are. Okay, I won't leak too many of the questions. So we are going to, so now that you have seen that n-body animation is possible, let's look at some codes. So MPI n-body, how to add animation using GD, I already showed you that. Then I will show you threading building blocks. And in that, I will also show you MPI, OpenMP tasking. I found a very good presentation which I had seen before. It's one of the OpenMP gurus. Then a little bit on PVS and job submission. So when you finally run these programs for real, you will be running it on a cluster. So there are some commands you apply to run it on a cluster. Dr. Jairaj may or may not. I think he has an opportunity to run it this afternoon. He will be running the n-body. Is it on? Maybe raise a bit more. Okay, that's good. Okay, so the equations that we are going to solve are gravitational equations. Basically, the attraction force between two masses is proportional to the masses, the gravitational constant, and the square of the distance between them. The form in which the authors, many authors write it is, instead of writing the square in the denominator, inverse square law, so in the denominator, they write the cube modulus, and then they multiply it again with the separation between the vector position vectors. So that way you get the three-dimensional subtraction done correctly, and you can also add the sign saying is it attraction or repulsion. We know it is attraction. All the signs work out. If you doubt that this, the basic structure of the equation is all known to us. That's how two bodies attract. Whether the sign works, you put in one object at location 2 and another object at location 4. Then 2 minus 4 is negative. That is getting corrected. So the force on Q will still point towards the positive. So I check the signs. That's how it is set up. Okay? Conventions need to be understood. Then the basics of n-body simulation says if you have a collection of n-bodies, the force on each is, there is no auto force. A body doesn't have attraction or repulsion on itself. They're like point masses. They don't have any effects on them, but other objects contribute. So do the summation for anybody other than myself of that equation. N-body problems are widely studied in HPC. I'm an amateur at that, I will tell you that, because I've seen real pros of n-body give hours of lectures on n-body. It is one of the most celebrated problems out there. We all have the mental capabilities, so if and when I get a research opportunity, I would deep dive into it and learn it well, no problem. The main n-square cost, because you have n objects, there are n choose 2 combinations, which is order of n square. So most algorithms end up being order n square force calculations per iteration. That's what I'll show today. There are Barnes-Hutt and other algorithms which have a certain cutoff after some distance. They come to n log n. Even n log n is bad, because if you have 1,000,000 objects, then the cost is 1,000,000,000. Log is 1,000. So fast multipole methods are used to get almost a linear cost, and those are the ones that should be used. There is an article in Communications of ACM, CACM, which is one of the flagship journals of computer science, where Dr. Bill Grob introduced this topic, and it was followed by an article by Richard Wooduk and his student Aparna Chandramouli-Sharan, and this was an extremely good article. I have read it once, I need to deep read it. That would be your best chance to learn fast multipole method is locate Communications of ACM and read the special article by Bill Grob, who introduces n-body. It came a few years ago. Okay, so they are going to, this is Pacheco's code, and this code is really good. I read it carefully and liked it. Velocity and force are going to be used in the various equations. Velocity is ds by dt, s is the position. Force is mass times acceleration, m is dv by dt. So they are going to have equations like that in this system, in the program, and they are going to convert it to a recurrence of that kind. Velocity at time t plus 1 is velocity at time I plus time delta multiplied with the derivative of the velocity. So that way you keep updating velocity. And positions are updated by taking the current position and time delta, which is h, multiplying with velocity. So the basic problem of n-body in this simplified solution would be to do this for every time step, update the position, and every processor or thread that is doing this calculation should know the current positions. They will do one more delta, etc. So the algorithm goes like this: a serial solver, which is what my animation was based on, is get input data for each time step, occasionally print the output. For each particle, compute the total force on Q, then update the position, and keep doing that till all the time steps are done. And finally end with the final position and velocity. So the main part, I just extracted the main parts of the code. The code is pretty readable even independently. So the force calculation loop is found in Pacheco's code. He arranges it such that we look at the so let me back up. Writing it in shared memory, writing it in serial code is kind of easy because the full data structure is visible. Writing it in shared memory OpenMP is easy too, because every core knows the full state through shared memory access. Writing in MPI will become tricky because you need to communicate information from the current node to the other. So the communications had to be designed properly. So this is MPI code, but still very simplified. We will look at which MPI node knows how much info, how much do they exchange in a minute. But barring that, the algorithm is, if I'm not the particle, k not equal to particle, so it's not a self calculation, then force of the particle is I forgot the sense. They are basically computing the current particles Sx minus F. Okay, so current K. Okay, okay. With respect to part and K. Okay, part and K are the comparisons. Okay, for every K. So we are computing the distance that separates them in the x and y coordinate. So this is a two-dimensional problem. And then it is taking the square root of the quantities, x and y, there. And then it is doing the denominator. I showed you that the denominator was a cube written in a modulus. So that's how it is written. The mg part is being calculated. Minus is incorporated here, minus a gravitational constant, current particle mass, and the other particle's mass. So the M1, M2 product and gravitational constant, they are all written. He calculates a lot of intermediate steps. It's pretty much the math equation being done step by step. So basically, yeah. So it's essentially calculating the forces, adding the forces experienced by the current particle with respect to all the particles in the summation loop. That's all what is going on. So that big sigma that was in my second slide as to the net force experienced by a given particle from all the particles is being summed. Okay, then comes, this is the animation I wrote. I'm showing you what the detail is. So in the print loop, you have a write frame. There are a lot of 5, 6, 7 GD commands I use, which is a fairly rich library. So you can write a frame. So it's like a little movie that you're creating. I'll supply the code. It's put up also on the class site. And then, the way, okay, this is the actual product of process of producing the movie. Compile it with the GCC, lot of other additional flags, JPEG, blah, blah, blah. I think GD library needs all that. Then convert it to MP4. These things are free software here to get. And then use QuickTime or a Windows movie player and play it. So the author says, okay, particle X has a certain force with respect to particle Y. Y will experience the same force in the other direction. So there is a choice of using only half the force calculations, because if X has a certain force on Y calculate the force of Y on X, we could reuse. This is exactly what we do in sequential programming, compute only half the cost if there is symmetry. But only if it makes sense. In a parallel context, don't do that always. Why? You have to ask yourselves which is costlier, computation or communication. And we will be surprised in multi-core that communication very quickly becomes more costly than computation. And so when that threshold is reached, you should recompute. So all the current wisdom of don't recompute redundant expressions goes out of the window in many cases in multi-core. Because imagine you calculating half the force and you want to reuse the force that guy has with respect to me, because he has calculated the force that I am exerting on him. You have to have a communication either through shared memory or MPI. That is bad. So don't do that. Recomputation often makes sense than trying to reuse data that lies a little far away electrically. So we will come to that point again, okay? Because this has been emphasized by many speakers, and we should see some jarring numbers to make sense, absorb that properly. But coming back to the code, n-body is going to be an n square operation per time step, and then so many time steps are done. So every MPI node contains a certain number of particles. That's a local n. N is the global n, which is all the particles. N step simulation, current step. Current local particle is named this way. Output frequency, delta t. Current time t. Masses, all the masses. And this is lying in the main. And this main is going to be run by all the ranks. So all the processors, all the nodes know all the masses. So mass is globally available, okay? So that's the info. The mass array is known, the masses of all the particles is known as a constant table, I would suppose, in every node. So it's a replicated read-only data in every node. Then you have local position, position of all the particles. Okay, again, that is also known to everybody. So if you have a mapping from particles to position, that entire mapping is replicated. This is to simplify the code. In more advanced code, I doubt that we could multiply the memory out like this. But there is still some communication. The velocity and forces are not replicated. So at least the code is going to show you some cleverness in terms of communication by having only a notion of local velocities and forces. And when the local velocities and forces are recomputed, they will communicate. Thus, I mean, let us see the code. That's how it goes. Velocities of my particles, force of my particles. Then it has other options also. So I'm just giving you a feel for the code. You may want to deep read and use this in your work. You don't need to remember all this. But we'll see the use of MPI collectives very nicely. That was a item of focus yesterday. We looked through many collectives. Collective laden code is important. Okay, so we get the arguments, parse all the arguments, then broadcast all the parameters. So all the processes are participating in the broadcast, and the root rank is broadcasting it, so everybody else gets it. Then I'm just stepping through some of them. Get the initial conditions. So the system, again, rank 0 is going to acquire the initial positions of mass, coordinate, y coordinate, etc. Could be a file or whatever, and then it broadcasts. Bcast with respect to rank 0, and it's also going to use scatter. Why is it using scatter here? Let us see. So scatter will chunk up the data so that each destination gets its own piece, as opposed to broadcast, which broadcasts the single data across everybody. So what is getting scattered? The velocity. So everybody will get to the velocity component. We have to read the full code, but that's what is happening. Okay, so the get initial conditions. Yeah, I mean, I think I went through this, or no. Gen initial, what did I do? Get initial conditions and gen initial conditions. Okay, this is the gen initial condition, which is the other case where the user wanted the random initial conditions to be generated. It's a similar deal. You randomly generate the particle velocity and all that, and broadcast as scatter. So no big difference. It is get or gen. Then, yeah. Then when I was reading his book, I said he's not going to reuse the force, and sure enough, later comment told me he's not going to reuse force. So compute force, compute the total force of the particle, log part. Don't exploit the symmetry. Okay, so I knew you won't exploit symmetry. Exploiting code symmetry will destroy code symmetry also, which is bad. code will start looking special case. Oh, I have the force, he doesn't have the force, you have to then detect. So it all destroys the nice SPMD read of the code, and it's code maintenance headache and performance-wise bad. So I'll get into some details pertaining to that, just to stick this point. I think we are trying to learn principles and get the experience of reading code, but the principles are more important. Yesterday there were some questions on parallel complexity, and good questions. So these questions make me go and revisit something I hadn't looked at. So I looked at PRAM models. Yeah, it's worth reading. Parallel random access memory is the topic that has been used. It's a hypothetical machine which has the magic power of having n processors and n memory cells, and has the magic power of concurrently reading, concurrently writing, or concurrently reading and exclusively writing, one of these models. And suppose you had this magic machine, how fast would your code run? That's what PRAM model people calculate. And it gives you a good feel for how a real algorithm might also run. So that's the general thinking they have. So unless you have a model, you can't analyze. Not perfectly explain all situations, but having some model is better than having no model at all. So that's the thinking in this area. Okay. And our model that we looked at, the work and depth model, is pretty popular these days. I haven't seen that work and depth model being questioned. Many people like the work and depth or work and span, because it clearly explains for the dependencies in a program and allows you to analyze. I'm not a specialist in this, but this is my growth path. If I'm looking forward to where I want to be better at parallel computing, I know where it is. I have my coding skills kind of under my belt. The rest my students will take care of. But I need to know how to design parallel algorithms, and how to explain my students how to design parallel algorithms. And I don't like any of the approaches because I'm just very strong-headed. I used to work on hardware design, hardware high-level synthesis, and we have designed fun parallel programming languages to express hardware behavior in, and then we used to synthesize circuits. That's a good experience because hardware is extremely concurrent, and we know how to think clearly in that domain. And I do see that many of the primitives in parallel computing are parallel actions. So that thinking, when reapplied in future research, might be the way to go. There could be some diagrammatic programming, etc. Visual programming notations often make sense. If you have not seen Petri nets, that's another visual model for concurrency. So expressing concurrent actions as Petri nets, which I don't have time to draw, but it's basically circles and transitions, bars. So two circles. I can draw a quick Petri net. Petri nets are one of the earliest models of concurrency, invented by Carl Adam Petri. When he was forced to fight for Germany, he didn't want to fight for Germany. He was conquered and put in a prison, so he had nothing to do. So he invented Petri nets. He's a great scientist who is no more. So Carl Adam Petri's model had diagrams like that. So which means process A has reached here and has put a token. Process B has reached here, has put a token. When they have both arrived, this transition can then fire and then can put a token in a place called C, which now might be fought by two transitions, T1 and T2. That is how you show arbitration. So in this little diagram itself, I have drawn synchronization and arbitration. So before they rendezvous, nothing can happen. Once they come here, it can go either way. So like that, diagrams are very useful to get the concurrency structure laid out, etc. This is a small digression. I think good algorithms are needed, but a good way to teach algorithms is also needed. We'll come to n-body in a second. I just wanted to finish this friendly little digression. So we were in communication complexity reduction. Let us finish that off. It's a very important decision, even though it's a one-line comment. What lies under it is like this. I like this slide a lot. This is from Intel's Arch Robinson. All these things come my way, and I grab hold of it and they keep it. So if you were to draw registers, caches, level 1 and 2, and memory to scale with respect to their actual sizes and the bandwidths they support, this is how the diagram will look. Registers will be this little dot. They will have a very fat pipe that connects them to L1 cache. Short and fat, so low latency, high bandwidth. L1 is this big, and it has a somewhat impressive width, but the distance has gone up, you see. This is then L2 cache in proportion, and that's the size. And its situation, let us now assume L3. Its situation with respect to the main memory is like drinking through the tiniest straw you can get. And the actual numbers will come in the next slide. And the main memory size would be 16 by 4 feet for 2 GB when drawn to scale. Okay, so this diagram can be put on a humongous wall. And then you need a telescope to see the cache, etc. So this is the disparity of sizes. So this kind of reminds us that we can't communicate across L2 that easily. Communication through memory is horrendous and all that. This is another diagram. I have these in the slides. So somebody has dug up this nice diagram. In a socket, registers are less than a nanoseconds in terms of access. L1, 3 cycles. L2, 12 cycles. L3, 38 cycles. QPI transfer 40 nanoseconds. And DRAM is in the nanoseconds. So it keeps jumping. Yeah. So communication is bad. This is another thing. I mean, these are all lying around. You can look at it. Okay. This is another remark. Since I have all these great speakers who spoke before me, I can say Bharat Kumar Sharma said Biotronic sort is great. And he just left it at that for GPU. And again, it makes sense. So pick up on these little points that they accidentally said. If you do the complexity analysis, it's there's a 2 missing, n square log n. We know that sorting is n log n for serial optimal complexity. Why do n square log n? Well, in GPU land, the parallel complexity land, it's the work depth or work span model that makes sense, not the standard big O n, and there it shines. So I think the whole communication complexity game is different. Anyway, so back here. Okay, so we did a digression. We said we have the masses known to everybody, and we only will recompute the positions and force, I think. So I showed a serial loop. This Pacheco's NBody code. Let me see. I'm seeing the code out of context. I just wanted to point to the key structure. This looks very similar to me. Update particles. Okay, so update the velocity and position for the local for the particles. I think the computation of the force. Okay, I'm back in sync. So each node computes its. It knows the masses of every other particle, and it knows the force being exerted on the current on the particle it owns with respect to all the other particles. That's a replicated array. So then it computes the position, recomputes the position, and then it has to update the velocity and position for all the local particles. So there is some communication involved. Yeah, I think I didn't get through all the code. There are some collectives used. I like to leave it at that. I can show the actual code if you like, but there is a certain design that is used. I wish I had put the whole code. I forgot. Maybe I was time multiplexing with other things. So let us see. So MPI, NBody, okay. Okay, this one, yeah, let's read it. It's right here. So compute force. So let's read the main just to make you happy, I hope. So main was declaring the local variables, init, com size, com rank, get args, masses, they're all spread. This is interesting. I wish I was going to read the code at this point. This is just a fancy thing that Pacheco chooses to show. It's not very useful in this code, but it's good that you know it exists. So you can create your own types in MPI. So if you want to refer to a certain type using other MPI types, you can create that and commit it. Just so that if you run into it in another code, you know it exists. So here it is going to take a dimension which is 2 in this case, take an MPI double. So 2 MPI doubles are going to be packaged up as a new type. It calls vector MPIT. That's the name, it anoints it and then commits it. So from then the MPI system knows that that type exists. So type create, type commit. So you can create, using MPI types, newer types. The idea of using MPI types is that these types are innately portable across machines. NDNS doesn't bother it, and things like that. So you can build more complex types and commit it. Then you should not forget to free it later. There's a type free coming later. That's the main thing that I picked up from here. Another MPI feature you learned. Output state. So this is the, okay, so this is the actual code. Sorry, I was stepping through serial code. Okay, so the time iteration is, it's a very short piece of top level code. So this is where it starts. And we can read it and we can look at the ISP diagram. So that'll be fun. So start the world, start the time measurement, print the outputs first, go through some number of time steps where you keep doing that little movie I showed you where each frame is calculated, objects are moved. So what do? You take a step number and delta t gives you the current time, right? So if you are in the 10th step and you have a delta t, that's the current time you are at. For local particles equal to 0, local particles less than local n, local particles. So sweep through all your local particles and compute force, which presumably tells you more about how the forces are computed. Let us read it. Very well documented code. So compute force, it tells you the ins and outs. Local particle, the particle in the local node. Masses, it's a global array. Positions, global array. So these are all globally known. N is globally known. N is the log n is the number of local particles. And outcomes in this calculation, array of total forces acting on my particle. So based on these input quantities, it is able to calculate the forces that are acting on the local particles. Forgive the details not being presented here, you can go back and figure out. So the purpose of the routine is to, given all these inputs, to know what forces are acting, and the compute force function itself is going to be familiar, at least in structure. So what it is doing is, now it knows how many particles there are in the whole system, n, and it has the ability to look up certain global information and execute the Newton's equation of two particles having a gravitational force, and it updates the local forces. So it comes out. So again, it's done in a structured way. So that's where we are. Somehow we have computed using Newton's equations the local forces. Then the update particles. So now we need to do an update operation. Let us look at that briefly. We know the local index of the particles. We are updating global array of particles, etc. We know enough about the world. Let us look at what the main things are. So it's basically applying the delta t times velocity. So it has the ability to look up the velocity vector, apply the update with the delta t. That's what it is doing. Update the position and velocity. Update the position and velocity of the local particles is what is happening. Okay. There is enough info. That is what it is able to do. Okay. Update particles. Update particles comes here. So this is still the main loop driving the computation. Compute the forces, update the position and velocity. There is an all gather here. Okay, now everybody needs to know everybody's new position and velocity. So it sort of does not a gather, but an all gather. Gather but then make it available to everybody. So that's a big funneling operation. These collectives are, again, like I told you, very complex operations, hauling a lot of bits across the network and highly optimized, taking advantage of the networks that were presented earlier. Manmohan was mentioning some of the networks that were involved, and you also mentioned MPI in one of the network topologies. So they are all topology aware. These collectives are highly optimized to the topologies. In fact, the problem of optimizing an MPI program or an OpenMP program for a certain topology is a research problem. People are doing it. If you have a certain communication density between certain nodes, and if you have a certain topology, how can you remap the nodes such that the topology gets used? These are all. And networks eat a lot of energy. So you have to be very friendly to the amount of hops you go through and all that. I don't know the figures, but there is one person in Germany who very much optimizes the amount of energy consumed by network. Thorsten Hoffler is his name. There are a lot of tricks. So one can do it by saving on the number of hops. One can do it by data compression also, like I once mentioned. Floating point data gets compressed, lossy or lossless. A lot of energy. Okay. So anyway, so that's the altogether is a serious operation. It is one where bits are flying all over the system, and maybe the fans will come on, like he was mentioning at that point. Yeah. And system faults also happen there. I heard talks from Argonne that when the system is extremely busy and cooking in one of the steps, when there are thermals or power bumps and variations or an alpha particle strike, systems can crash also. So very correlated. All right, so, and then finish up. So the structure of the code is clean enough that you can go back and read. I had to spend some time quietly reading in the morning, and I got it. You can also do so. I don't expect you to share my mental image, which I have lost by now. It's a 3-hour half-life here, it evaporates, but you can get it. All right. So let us look at the structure of the program when it's executed. That's what is important. I hope I kept it here. So I have all the session slides today. I have 2 session slides for session 17 and 18. This is supposed to be session 17, so I put it in session 17. Yeah, I have that. So ISP UI, log, MNB. So again, since I have given you a friendly tool, I run this tool. I wanted to show this to Manmohan too. So we have this visual tool that traces MPI using PMPI and then builds a postmortem trace, and it tells you the structure of execution, including the line numbers. So one can pretty much keep this in a window and the text in a window and know what are all the initial broadcasts, and then gather and all gather. Then it's all gather, all gather, gather, all gather, gather, all gather. That's what the code is doing. Yeah, there's a lot of hidden. This is source, and I told the people how to get it also. There's a lot of stuff here. So one can even select 2 windows and look at intra-CP. So it even has happens before structure, which is the allowed overtakes between MPI calls. I didn't show you this. There's a lot of little hidden details here in this tool that allows the tool we built to reschedule whenever needed. So this one command being able to jump over the other command, that partial order can be seen in many cases. Anyway, this tool needs improvement. It is a 10-year-old tool. It still works like a toaster when we implement it. That's a nice tribute to the students. Okay, so we can see where this all gather is coming, and we can pretty much step through the code and see where these. So this is MPI and body basic. So where is this gather? Gather is line 353. All gather is line 153. So 353, 153 is dancing about between those 2 lines. Let's go to line 153, and what is it? It's an all gather. So it's an all gather for the position and forces, I guess. Yeah, 153. That's where it ends. And 353. Again, just to see that that's where the execution dances about is useful. 353 is here. So MPI gather. So this gather is being done by who? Output state. Okay, output state wants to gather. Output state is being done by the root node. So it gathers and prints. Okay. All gather is sharing the forces yet again. So it just oscillates between these 2 steps. at least there is some confirmation that the computation is being achieved. With some data replication, the computation is being achieved with a decent amount of communication between the nodes. Any questions or remarks, or is the general structure of the n-body program more or less clear to you? I mean, not that you need to say I can sit and code it now, but are you think you can go back and read something like this and figure it out at this point? That's the reassurance I want. Okay, this is 2 hours of study on your part. Try this tool. You should be able to program it. That's the level I'm hoping. Yeah. Excellent. So if that's the level of understanding we have now, I will try to speak in between. Okay. Okay, so how do we actually submit this and run it? PBS is what we have here. Utah discontinued PBS. It uses Slurm. It's open source, like you said. But Utah says Slurm system when you submit PBS, it remaps everything to Slurm. They're so similar. So it on the fly generates a Slurm script when you give a PBS script and then runs it. Not bad, right? So they don't need to buy any PBS. Yeah.
After this,
yeah.
Or an expert,
Yeah.
Will not be comfortable at all in the computing. So whatever command lines they get from the beginning of their coding age, they get adapted to it.
Yeah.
So changing that to Slurm is very, very difficult for them.
I know.
So having a wrapper on top of Slurm is always very easy.
It's good. I don't know how many errors it throws and whether you need to reflect the error back to PBS level. Probably not much. Like shell, you know. So I think I mean when you have huge translation hierarchies, sometimes mapping that error back here is an issue. But in this case, it doesn't seem to be that issue. It's just small syntax and all that. Okay. So that's what it does. So this is how you write a PBS to submit the n-body. This is probably what you'll do in the afternoon. So you will write a bash like a bin bash. You allocate a certain quota of compute time. I'm very new to PBS or Slurm. My students just wrote this. I barely know. But you are requesting more than 4 nodes. There's a certain way in which you have to tell PBS to save the output and standard error. So based on the job, it will create file names of this kind. That's what it does. So if you have 10 processes writing or things, you can either get a job ID based file name, or you can get more richer file names manufactured for you. And you have to give this is School of Computing, King's Peak, that's the node. You have to give the A and Q. I think there's a Q and there's an A. I forget these. Professor Jayaraj knows, or does anyone know here from the supercomputing side? Q name. And A is for something. It seemed to work for Jayaraj. I gave literally this. Authentication or something like that. Okay.
Actually, it doesn't do anything, but it records.
It records.
That is for School of Computing and
Okay.
by keeping.
Okay.
Like that.
Okay. Things like this. We do things like this, and sometimes we request for every job. We submit 25 jobs and ask for an Intel compiler. Then it comes back saying that we don't have that many licenses. Things like that are funny. Yeah. But some of the commercial licenses or public licenses don't give us any issue. All right, so then we do CD MPI testing. So this directory has to be present in the root node. Module load, GCC, OpenMPI. This is what we requested the system. At that point, these become available. Otherwise, it does not know anything about GCC or OpenMPI till then. So there are module query commands. Then you do MPI CC, MPI n-body, basic, math, MPI run. That's pretty much it. And then it goes into an unknown world where after some time you can watch the job queue. Okay, so at some point it comes back from the queue with all those output files created. I experimentally tried on a multi-core cluster and wondered what parameters you may be running today. My guesstimate is that you will be asking for 128 nodes. I don't know whether that is going to clear quickly. It's not clear how busy your queues are. I have no idea. Some queues are. And best to name it not error out, but put a different binary. Maybe the n-body problem will have 32K and particles for 10 time steps, etc. Don't make the outputs very frequent. So the output frequency is deliberately set higher than the number of time steps. So do something like that. So the code doesn't output at all. And then even put the full output to dev null. So you're kind of getting good timings, you know. This is my best guess on how you might get reasonably good timings out of your run. And it prints the MPI start stop time, okay. This is not done. I say closing comments, it's only for this slide. Remember, I have threading building blocks. So please perk up a little bit more. Good food is waiting, but I'll. Okay, this is just to closing comments since I saw that. I think in HPC and parallel computing, you need to learn hardware design and basic gates and power well. I'm striving to be a good coder even now. I used to be, but not anymore. But tool users, getting as many tools understood is useful, etc. Okay, so let us now set my sagely advice aside and look at real things. Okay, session 18. This is fun. So what is threading building blocks? I want to give a taste of threading building blocks. I can go on for longer, but we don't have time. But I'll show you enough about what distinguishes it from other libraries and methods we have seen. Okay. And this is borrowed from Rafael Asenjo, who gave a nice tutorial recently. I wrote to him, got permission to share his slides. Okay, threading building blocks is Intel's own creation. It has now been put on Apache license, available to the world. It's open source. It is basically a collection of class libraries. That's the nice thing about it. The first thing to know is that it doesn't have a separate compiler like an OpenMP compiler. It is going to use C++ compilers. You have to be up to a certain standard in the C++ to use certain features. So if you want to use C++ lambdas, you have to be C++ 14, I think. Once you have a GCC that works at that level, you can use lambdas. Otherwise, you have to use function objects, which is the old style, etc. But otherwise, it's a whole bunch of very well written C++ template class libraries. That's what it is. So in that sense, you are not getting another runtime or anything. The main ideas there are work stealing. We will look at a nice PowerPoint animation of that, thanks to Rafael. We will look at some features of how parallel for and reduce are supported. We will look at some interesting other concurrency structures such as pipelining. So if you want to have an assembly line where you have a pipeline of actions, one enabling the other, you can define that pipeline directly. Or if you want a task graph where A finishes, then enables BC, BC finishes, enables D, you can write C++ chunks corresponding to A, B, C, and D and stitch together using stitching primitives in C++. So it actually executes that task graph using work stealing and all that. So it gives you more flexibility than just going after loops. You can have task graphs and other patterns. So there are 8 or 9 or 10 different patterns that are in this McCool book, or maybe in a dozen patterns. All those patterns have nice support here, like the map reduce pattern, the scan pattern, parallel prefix sum pattern. So it's richer. Yes, okay, this is his initial slide. We know it by now that we have to provide more mechanisms to exploit multi-cores properly. Parallel frameworks, this is a good survey-ish thing. So what else other than MPI are available? There is something called SHMEM. There is something called GasNet. There are a few others. I don't know much about these, but they exist. Some of these are message passing, but underneath, but giving a shared memory appearance outside. I mentioned UPC long ago in the first class. That's kind of like that. It gives you a shared memory appearance, but message passing is what makes the messages move. Then in this ilk, we have pthreads and OpenMP, which we looked at, Intel threading building blocks. For Microsoft, they have Microsoft's task parallel library. For Java users, there are Java concurrency libraries, very well supported. Intel had something called Silk, which was Charles Lyserson's company. Intel bought it and now used to have it as an Intel product, but they are not maintaining it. Whenever you see Silk somewhere, their advice is go use OpenMP now because OpenMP is good enough. It has similar features. CNC is still around. It has a following within Intel, etc. I won't go into all this. There are too many of these. Task frameworks are much lighter weight than thread frameworks. This is the key message that I'm going to convey today. Why tasks? Why not threads? Tasks are much lighter, and thanks to Ruud van de Paar, whose slides I'll show, you will understand tasks extremely well. I understood tasks for the first time only by looking at Ruud van de Paar's slides. I'll show you those. Extremely good slides. It can't be simpler than that. Okay, that's good. But TBB, Linux 18x faster to start and terminate a task compared to a thread. So there are advantages. So tasking is basically creating work items. Think of it as a function call plus some work description. It's not the OS thread that picks up and runs it. It is your own task scheduler, which typically is a user level, user space program. There are some problems with task schedulers. It may not be fair like a OS scheduler, but you can get other biases like thread affinity bias. So if you are, things can be, okay, it can schedule based on the size of the work that needs to be executed. That can be a priority factor for a tasking scheduler. Big chunks of work might be given a priority. That the OS doesn't know. OS really is a kind of blind to your application semantics or data size. So you can build in some scheduling magic that makes a task scheduler be more aware of your circumstances. So creation of task and threading, I don't need to look at this. This is Apple's Swift, which kind of many people use. Okay. Okay, so we have to look at Ruud van de Paar's slides. That's when you understand tasks and threads extremely well, hopefully in 10 minutes or so. So let us look at that. He's from Oracle. And he actually shows it in the context of OpenMP, so that's nicer. So we understand how OpenMP's tasking works, and the advantages of tasks are also reflected in other languages like that. So dial back to OpenMP, understand tasking, we'll come back to TBB. Since you know OpenMP, it's easier to understand tasking here. Okay. This is the general idea, a picture. A thread can generate a whole bunch of tasks. They lie in some queue structure, and other threads, maybe even this thread that generates the task, can pick up one of those tasks and execute it. So threads population need not grow and shrink. You can keep a certain population of threads, and threads can steal tasks and execute and move on to the other task. So that way threads oversubscription need not be done at all. You don't need to create 200 threads in a 8-core machine or anything. You create the right number of threads that match the hardware, and then lot more tasks can be created. And then the threads can, based on the opportunity, steal from each other. Okay, so that's where we are going. Who does what and when? Developer, use a pragma to specify where the tasks are. So this is how in OpenMP itself you can write tasks. OpenMP runtime has now the ability to do work stealing and fancy things like that in some modern OpenMPs. When a thread encounters a task construct, a new task is generated. We'll see an example. The moment of execution of the task is up to the runtime. And this is how the pragma OMP task will look like. Some of these are Fortran. So the kind of things we need are the OMP task, OMP barrier, OMP task wait, flush task wait. Okay, so this is the best part of his presentation. We'll look at 4 or 5 slides which have nothing but print statements. Then we'll understand how tasks run with respect to threads. That understanding helps understand TBP a little bit better. So write a program that prints either a race car or a car race and maximizes parallelism. It's funny. Okay. So he writes this program, main a race car. We'll get to, so it only prints one of the options. It doesn't print a car race, it prints only a race car. It's serial code. What will this program print? A race car. Okay, check. Now we are going to change it. Main pragma OMP parallel. How many threads were there in the previous? I didn't mention. Okay, it's a serial program anyway. So using 2 threads. Okay, so this is what it's doing using 2 threads. Okay, so 2 threads are launched as a thread team right here. Okay, and 2 threads are going through these print statements. Prints are brittle. You cannot pound on print statements from 2 threads. Sometimes you do bad things to the buffers associated with prints. But assuming that doesn't happen, you will get all these things. AA, race, race, car, car, because 2 threads were launched and they had to both do a race car. But it can get interleaved, a race, car, a race, a car, race, car, or a race, car, car. Okay, so these are all what happens when you just join a launch 2 threads, and threads are, he has not observed many of these, but that tells you what threads do. And there's a way to create the number of threads also. Okay. Now he adds, he's nicely, delicately tuning this example. So now he has OMP parallel, and then OMP single. So the thread team is going to start 2 threads, but single, as we remember, only 1 thread is allowed to go through the single section, the others flow around. So the output will be just a race car. That's it, even though we have 2 threads. Okay. If I'm going too fast, let me know, but otherwise. Now what is he doing? Now he's introducing tasks. This is how you write a task. So pragma OMP parallel, pragma OMP single. Okay, so even only 1 thread is allowed to go through the single section. Now it is encountering tasks. So that single thread can create tasks, work items. So that's the idea. So even though we have one thread, it is able to create race and car as 2 tasks, which will be picked up and executed by the OMP runtime. You don't need to have manufacture your own threads to do it. OMP runtime will polish off the tasks eventually. Yeah. So let us see what it will print. A race car, a car race. Multiple executions. And why did we get all that? Let's see. So race and car are put in tasks. So and the task execution order is not specified. So A gets done. I don't know whether A can get delayed by the print buffer, because there is no, I don't think there is an obligation to bring out the A before the race or car, unless you do a flush and all that. But anyway, we don't need to get into that. Okay, so it looks like A is getting printed first and then car. Okay, task can be executed in arbitrary order. That's the message here. But a thread can create tasks. That's also shown here. How the sentence end with is fun to watch. Okay, now he is saying do more by having is fun to watch. So now he is adding some more. Print A, pragma OMP task race, pragma OMP task car, then print is fun to watch. So it is the single section where the single thread initiates the print A, creates 2 tasks, and then goes and executes printf. So the threads themselves, the thread itself is doing these 2 prints, and the tasks will get picked up and it'll do. So let's see what happens. So A is fun to watch, race car. A is fun to watch, race car. A is fun to watch, race car. Is car race. Okay. Car and race can swap. A and is fun to watch are two prints. Somehow that A and fun to watch are not getting oh, car race. Okay, fun is fun to watch. That's the full word. Okay. Again, I'm not. There are safe prints. Okay, so C++ has a thread safe print. If you didn't know, you should seek it and use it. Then you can printf from multiple threads. Although it's not a good habit, if you want it, there is a thread safe print, which has the right locking for the print buffer. But this is just a simple example. Okay, so what will now this program? What is that? Okay. So now he's saying pragma MP parallel, pragma single, task car, race, task wait, and then is fun to watch. So the tasks have to wait. So a car race is fun to watch. A race car. I don't know. I haven't remembered all the other things I saw. I don't know how much of this I need to execute. The point is made that tasks are different from threads, and tasks can be created by threads. That's the thing I wanted to get out of this presentation, because this is nice. Somebody wanted tasks anyway last time, and why not see it in OpenMP context? Okay, so now we'll look at what the TBB runtime does. This is Ralph Asenio's presentation. So he says that in general a TBB program will have threads. Then most of the TBB program doesn't look to contain any threads. You don't explicitly create any thread team. Whenever you run a TBB program, you are executing various structured constructs in it, like a parallel reduce, parallel for, everything. So when you execute those, automatically the requisite number of tasks will get created for you. Tasks will get created for you. It will be picked up by the right number of threads. There could be ways to parameterize the runtime to have some threads, but typically you don't see it in the code. But this is what happens. Task gets created by some program thread. Okay. Task will go into a global queue, and then there are worker threads associated with the TBB runtime. So this might be how the tasks are. The worker thread can steal a task. So in the TBB runtime or in any tasking runtime today, task gets stolen, and this may steal it. This can create another task. It may hit another parallel for or parallel reduce, creating more tasks. Or it might hit a flow graph structure or a pipeline structure, one of these structures. Everything spawns tasks. Then this can go there. Now watch, there are some fun movie scenes here. 3 things. Okay, this even though it created the task, it says, okay, I'm going to execute it. I'm kind of free now. Oh, this is the stealing. So stealing happens at the end of a dual-ended queue. So the creator of the work has no locks in many cases. It puts the work in its queue, and without any lock or a very lightweight locking, it can absorb the work back. The thief has to take a heavier lock or a synchronization, so it pays the price. And the work stealing runtime arranges it so that thief typically steals huge tasks, so that the overhead is amortized. So they have some strategies like that to control how the load balancing goes. So this is how this is a nice animation. You can play it when you get a chance. So iteration ranges are the interesting thing. We split a large iteration range into small. I'll come to that. And then the small iteration ranges will be split further and further and further. And then the right-sized iteration range will be stolen by the right-sized thread. I will come to a nice slide here, not here, that you need to see before you see the rest of this animation. So how does worker. This is the dynamic chunking of woods. So what really goes on is dynamic chunking. So in OpenMP we had to declare chunk size. TBB you don't, and the chunk sizes are nicely determined by the system. So this little TBB program is all you need to see, even if I get interrupted and all that. If you understand this slide sort of, you will get a good flavor of TBB. So this is an entire TBB program. So sorry for the people in the back, you may not see it. I can try to magnify it. Yeah, I can magnify it. Okay. So you write TBB program as a C++ program. Then you include TBB parallel for.h if you are using parallel for, things like that. Start with the main. Start using C++ features. Auto types are nice. It types it for you. Type checking is very well done. Standard vector double 10,000. So you're defining a big vector. Then you are defining a mutex. Then you are going to execute a TBB parallel for. So this is how you write TBB parallel for. And what do you give it? You give it the iteration range this way. TBB blocked range. These details I don't need to explain. Basically you are saying, I'm giving you a range over which to execute parallel for. Big range, starting from 0 to values of size. You with me? So starting from 0 to values of size is my entire range of interest over which parallel for should be done. What do I need to do over that range? That's the next part you need to specify. What's the work I'm going to do? Am I going to increment every item, or am I going to do something else? That comes later. That is a lambda. This is how you write a lambda. Lambdas are anonymous functions. You don't name a function and declare it upstairs there and then refer to it by the name. Just write a nameless function when you want it. So lambdas are open close brackets. This shows the fact that all the globals are available by reference, passed by reference automatically. Then this lambda picks up a range called R. What's the size of R? That the TBB runtime is going to decide for you. So out of this big range, some range called R will be given to you, nicely chunked up. Once you get that, this lambda is happy and it will run. What will it then do? It will take a lock just to print carefully, and it is sort of telling you what's the range size r.end minus r.begin. Okay, that's how you know how big a chunk of work did I get. Okay, that's the beauty here. This is the full workspace. How big a chunk system gave me, that's the size. Then unlock. Then what do I do once I get the range? Oh, this is going to do the sine calculation. Remember we filled a sine wave on a range. So we are just going to fill that range with the sinusoids for that range and come out. So when we run this, this is what we get. This tells me pretty much what TBB did for me. So I gave a 10,000 range. I wanted to generate a sine wave over the 10,000 range. I said, this is my iteration space, which is 10,000 big. But here is my worker, which is this lambda. The lambda will be fed the range automatically by the TBB runtime based on what it needs or what its availabilities are. So it will give a humongous range initially. 39 is humongous, humongous enough, automatically, and then 39, 39, then the 19, then 20, 39. This becomes is based on the threads that are available to run the tasks, and the task sizes are automatically created. So the tasks are created in such a fashion that it even tends to run in the thread that owns the memory necessary to run the task. It even takes care of thread affinity. In OpenMP, it used to be the case that you have this first touch. You had to simply say a equal to 0 or something like that. Then you get the cache line pulled into you, first touch, and then you compute. You don't need to do such magic. This gives you affinity. So that's the beauty of this program. You can really see the chunking dynamically being determined based on tasking by the TBB runtime. Now back to this one. It'll finally finish up our understanding of how chunking works. So big ranges are given to you to run. This picture shows that ranges are split by the TBB runtime recursively. So if you are doing a parallel for, it chunks up using some principle. You may do a parallel reduction also. Then it does a reduction. So parallel for, parallel reduce are available. This is a nice diagram. Splitting goes on for a while, so you have created a gazillion amount of tasks out there, okay? Best choice for theft is there. Take the biggest booty out there. So if you have big tasks lying there, the thief is going to be asked to take the entire right-hand side of the tree. So that way the stealing overhead is amortized when you do that much of work. But the thief can descend there and work, but it may get stolen back, things like that. So work stealing nicely steals back and forth. The second best choice is like that. So the system knows how the tasking has been chunked up, the iteration space has been chunked up, and it prioritizes the task to steal in the right way. That's the main idea. So you can write, and then it is very careful to not overly chunk up. If it overly chunks up, you can add up the areas of all the blue lines. It is too much, right? All the white is useful work, blue is chunking overhead. This is better. So there is a little bathtub curve saying you can chunk and get better performance. Then if you start over chunking, the performance gets worse. So it has some awareness of how much to chunk. These are very, very good, and I showed you this already. Christopher Woods does the best job here. But I'll show you the rest, and we'll go eat. So parallel reduce is available, similar thing. So you give a range to it, blocked range, and then it does the magic of the reduction in that. You can do this pipelining. So suppose you have an input filter, read as a stream, process filter. This is like a DSP pipeline, process X square output filter. You can literally create this in TBB as it looks. You can write 3 TBB lambdas and string them together, some syntax. It runs it using tasking. So the three tasks will be involved there, and it'll run pipeline parallels. So this is how you do it apparently. I haven't written these. So you can write add filter, my pipeline add filter, my pipeline add filter, run it. Something like that. It's more flexible. Lambdas are available. Lambdas are used everywhere. Has anyone used lambdas in any language before? Functional programming or Python or things like that? Yeah, lambdas, and lambdas are in Java also now. Lambdas are almost there, yeah, in any language, because anonymous functions. There are some extremely good C++ EDMs which used to take a while loop and ugly conditional test and all that. They are now available as a single lambda you pass to a function. It's so readable outside, and it works efficiently. They are closures. Lambdas are just closed functions that absorb something from outside. The problem with TBB, biggest problem, it doesn't have a data race checker. That's a bummer. People have tried to run thread sanitizer on TBB programs. What they find is it throws a lot of false races at you because it does not know what goes on within the TBB runtime. So all those implied synchronizations are not known. When I read that, I knew this is exactly what we did when we created Archer. Unfortunately, you couldn't run Archer. It still works. In Archer, before creating Archer, we tried to apply thread sanitizer to OpenMP. We got all kinds of bad races which don't exist from the OpenMP runtime. So we taught thread sanitizer what the OpenMP runtime really is using annotations. Then it became a perfect fit for OpenMP. So like that, somebody has to come in and customize a race checker for TBB. Then because data races are, if you have a program that has a data race, it is equal to a program that has divide by 0 or equal to a program that goes out of array bounds. There is no lack of severity. It's the same severity level. So if you're not willing to have a program with divide by 0 or out of bounds, don't have a program with races. This is the unstated truth, unemphasized truth in parallel computing. Most books should just put a big red saying, here there's a code with race. Community, please help us, because these bugs are as serious, and we don't have tools. Unfortunately, detection of divide by 0 or overflow, all these are hard enough, but races are 1 degree higher in hardness. but we need to get rid of races. Races destroy the contract between concurrent execution and the compiler's work. Compiler's work is to optimize sequential code. That contract is broken. I showed them some examples where we wrote a handshake in Java, where we removed the volatile variable, and the program hangs. It's just 4 lines of code. And you should remember that example. If nothing else, you should remember how quickly that Java program hung when you remembered volatile. So when you put volatile there, those become special variables. The compiler cannot optimize across them, so they are properly synchronized. When you are properly synchronized, even though it is concurrent looking for the I, it is not concurrent in bad effects. That's what it means, okay? Concurrency is not bad. Concurrency torn apart with all the entrails or guts available to look at is bad. You can't go to get torn apart. Half state shouldn't be exposed. Parallel pipeline is available. I'm almost done. Flow graphs are available. So you can have input squarer, cuber, join, summer. So you can literally define this in syntax and throw it into the OpenMP TBB runtime. It runs it like that. This is how you do it. Something like that. Make edge. So it's almost like stitching a graph. Make edge between input to squarer, input to cuber, squarer, etc. So you can stitch the functions together, put it. It becomes a parallelized activity right off the bat. These are fun. These are available in a graphical form in Windows. So there is a TBB pointing to Windows, which is well developed, where you can literally click with the mouse and draw the edges, press a button, it generates a C++ TBB code and runs it. And I think that is how parallel programming should be. For many people, they should not think parallel programming. They should just stitch these nodes and put in pre-built modules. With that, I am done. If you need more, let me know. But looking at your body language, I'm awake because I'm speaking and I'm hungry. Sorry. Yeah. Anyway, thanks. It was a lot of fun all these days. Do Phil again. That was only the beginning. Playing Karodpati and all that. There are a lot of other things. So please do this and have fun. Okay. This is just to go through that. I did a best effort today of all the things I may have said. And I have the option to say, well, I may not have thought of enough questions, so you put 4 questions and answer it yourself. And if you find any typos or ambiguity in any question, that's up to you to define. You can change the question and answer what you want. Okay, so I'm giving you almost this is just to promote discussions and have some friendly conversation. You all will get. I can't tell you what grades, but you all will pass with high colors. Yeah. But this discussion of going through everything once is important in any course, so please participate in that. Okay. Okay, so this, okay, look at this. All right, okay. There are things here. You'll find, I won't spoil anything. I mean, this is my warped sense of humor, but if you like it, I'm happy. If you don't like it, ignore the humor. Okay. Thank you. I think we'll go and eat. Okay, yeah.